We're going to talk about the three properties of logs that we need to work with. We're going to focus on how to use the properties, how to write the properties, both written out as a sentence, but also as an equation. So we'll start with the power property. The log of a product is equal to the sum of the logs. Now that is sort of a shortcut way of saying it. What we mean to say is that the log of any base, so I'm not even going to write the base here, of a product of any two numbers, variables, constants, doesn't matter, is equal to the sum of the logs. And this is where that description is a little bit vague. What I really should say is the sum of the logs of the two factors. So the log of the first factor plus the log of the second factor. And no, there's no rhyme or reason to when I choose to make curly L's and when I don't. The key here is that the sum is that plus sign, and the product is referring to this multiplication. So if the property goes one way, it goes the other way also. And the first thing we do with these is we use the product property to simplify the log of a product by turning it into the sum of two separate logs. So the log base 3 of 9 times x, because 9 times x is a product, we can separate that log of a product into the sum of two different logs. Log base 3 of 9, which is the log of the first factor, plus log base 3 of x, which is the log of the second factor. And the reason why that's useful is that one of those pieces can be simplified. Log base 3 of 9 is 2. So I can write this as 2 plus the log base 3 of x. And notice how this is possibly a little bit different from what you would expect. When we take the square root of 9x, the square root of a product, we can take the square root of any factor times the square root of the remaining factor. So the square root of a product is still the product of two square roots. It doesn't work that way with logs. With logs, the log of a product is equal to the sum of two logs. And way back when, just for a fun little trip down history, before we had calculators that could calculate logs very quickly for us, what we would look at is a table of values that would give us a lot of basic logs, like log base 2 of all the prime numbers. And what we would do is use those prime numbers to approximate the log of a bigger argument. So if we take log base 2 of 48, and we can break it down into its pieces, well, 48 is the same thing as 3 times 16. So I can rewrite this as log base 2 of 3 plus log base 2 of 16. And we were just told that log base 2 of 3 is about 1.585. And log base 2 of 16 we know is exactly 4, because 2 to the 4th is exactly 16. And so log base 2 of 48 is approximately 5.585. And honestly, we don't use that trick very often, but it's nice to see where it comes from. We'll skip that other example for the moment. I'll leave it on the screen so you can pause and look at it if you want to. The next property of logs is super similar to the product property of logs, but we're talking about quotients. So this time, instead of talking about the log of a product of m times n, we'll talk about the quotient of m divided by n. And based on what you know about exponent rules, maybe you can guess the difference here. That if, when we talked about the log of a product, we turned it into the sum of two logs, because when you multiply powers, you add exponents. Well, when we divide powers, we subtract exponents. So maybe you would have guessed that this log of a quotient would equal the difference between the two logs. And so that's exactly how I would rephrase this. The log of a quotient equals the difference of the two logs. And if I wanted to be a little bit more specific here, I would say the difference of the log of the dividend minus the log of the divisor. But that seems like overkill. And so we can use the same exact logic to simplify log base 8 of x over 64 just by turning it into log base 8 of our dividend minus log base 8 of our divisor, or the log of our numerator minus the log of our denominator. And the advantage to this is I know what log base 8 of 64 is, so I can rewrite this as log base 8 of x minus 2. And that would be considered more simplified. A quick note about when you have a slightly more complicated argument, like in number 11, the log of xy over 2z. Well, there's products, there's quotient, there's a lot going on in here. What we'll do is break it apart one piece at a time. Log of xy over 2z. And I know there's no base there. We'll talk up next class about what it means to write a log with no base there. There is a base there. We'll talk about it next class. But we can write this as the log of the numerator minus the log of the denominator. But we have to acknowledge when we're not done yet, because both of those two logs are still a little bit too complicated. They're both the log of products. So we do need to separate both of those into the sum of two logs. And here's where you have to be careful. Minus the log of 2z, when we separate the log of 2z, we have to remember there's a minus sign in front of that whole thing. So that would be the log of 2 plus the log of z, but both of those things are being subtracted from the log of x plus the log of y. So I would have to make sure just for my last step to distribute that negative and call it the log of x plus the log of y minus the log of 2 minus the log of z. And so what we've been doing so far is simplifying the other direction, because remember, in an equation, it always works two ways. You can go the other direction also, and the word we use for that is usually condense. Condense into a single log means we want to take a bunch of logs, something like that, and just smush them all together until it's just one log, which means anytime your directions ask you to condense, it means your answer must be the log of something. One log, one argument. There could be a bunch going on in there, but when it says condense into a single log, you have to understand that single log means you're only going to see the symbol log once. So if we look at this example, we're going to take the log base 3 of 4x minus log base 3 of 12 plus log base 3 of pi. And yes, those are the logs of products. So we could simplify that by chopping them up into smaller parts. But that's not what the directions said. The directions said condense. So we're going to take the log base 3 of 4x minus the log base 3 of 12. We're going to take that and condense them because it is a difference of two logs. We're going to condense that into the log of a quotient, 4x over 12, which I will simplify to x over 3. And by the way, one thing I haven't mentioned in all of this, though you probably guessed it anyway, is all of these properties only apply if the base of the logs are the same. I can't take log base 2 of x plus log base 17 of 5 and put them together in any way. And so our final step here would be to recognize that, okay, now I have the sum of two logs, and I can turn that into the log of a product, pi times x over 3, and that would be my final answer. We would call this condensed, not simplified. I know it sounds weird that simplified is the long one, but that's what we call it. It's like with radicals. Simplified means chopping it up into the smallest pieces possible. And there's one more property to go over. And it is not any harder to do than the others. It is a little bit harder to explain, to say. So let's go slowly here, make sure everyone catches on. the power property of logs is that the log of a power, which means any number raised to any power, the log of a power, is equal to the exponent times the log of whatever that power's base was. Essentially what happens is the exponent comes in front as a coefficient. So that's where this p came from. And that's the way I'm going to rephrase it. A little bit less technical than the other ones. But I would say the exponent inside of a log, so that means the log of a power, can be written as, the exponent itself can be written as the coefficient in front of the log. It's a simple idea, but it becomes a very powerful tool. So, for example, we would take this 7, the exponent inside the log, and turn it into a coefficient in front. So that could be 7 times log base 9 of x. And that's all we're talking about. One thing to note, though, you've got to be careful about, you can only pull the exponent down in front of the log of the base that had that power to begin with, that had the exponent. So if we look at the next example here, 3x to the 4th, that to the 4th power has nothing to do with the 3. So I can't pull the 4 in front. I can't call that 4 times log base 7 of 3x. The 4 can't go in front of the 3 because they're unrelated to each other. So what I would have to do first is chop up the product, the 3 times x to the 4th, and now log base 7 of 3, there's nothing for me to do, but now I can pull that 4 in front of the log base 7 of x. And that is as much as I can do. And for the last example on this section of the notes, log of the square root of 5x squared minus 10, you might be thinking to yourself, we didn't have any properties about square roots. Well, you're right, sort of. Remember that one of the things we've come back to a few times during the year is that a square root is also an exponent. So the square root of 5x squared minus 10 is also the same thing as 5x squared minus 10 to the 1/2. We call those rational exponents. We remember the connection between the denominator of the exponent and the index of the radical, which in that case was the invisible 2. So now we can absolutely pull out the 1/2. 1/2 times the log of 5x squared minus 10. And it is tempting to say that's 1/2 times the log of 5x squared minus 1/2 the log of 10. It's tempting to separate that difference. But we don't have a property for the log of a difference. We can only separate the log of a product or of a quotient, not a difference like this. If you can write that as a product, then you could separate it a little bit more. Well, in this case, you can, so not fully simplified yet. What I can do is rewrite the 5x squared minus 10 as 5 times x squared minus 2. And then I can separate, because now there's a product inside that log. So now I can write 1/2 the log of 5 plus 1/2 the log of x squared minus 2. And if x squared minus 2 factored nicely, I would keep going. It doesn't.